Hi there. Welcome to the third part of a four-part series in cognitively guided instruction. My name is Janice Nowakowski, and I am a district consultant in the Richmond School District, supporting teachers from kindergarten through grade 12 in the areas of mathematics and numeracy. This series focuses specifically on cognitively guided instruction and connecting that to the BC K-5 mathematics curriculum. This third burst session will focus on multiplication and division. So what is CGI? CGI stands for Cognitively Guided Instruction. It is a research-based and sense-making approach to the teaching and learning of number operations. So addition, subtraction, multiplication, and division. There are decades of research to support CGI practices in elementary classrooms. The book that you see on your screen is sort of the core resource, Children's Mathematics, Cognitively Guided Instruction, and this is the second edition version. The first edition had a darker blue cover, just in case you're looking for it in a school library. So where do we find CGI in our BC Mathematics curriculum? It comes in many different places. It comes in the big ideas, in the competencies, in the content. We think about the connection between CGI and algebraic thinking and different types of equation types and structures. And you can see here where the arrow is pointing to, I think this is grade 4, one-step equations for all operations. And in our curriculum and the elaborations, it actually uses the language of CGI, start unknown, result unknown, change unknown, the different types of structures for addition, subtraction, multiplication, and division. Many children only see result unknown, that sort of something times something equals what. And so we need to play with those different equation structures to expand children's thinking and understand the relationship between multiplication and division. On the bottom left, you see some of the curricular competencies that support cognitively guided instruction practices. Develop, demonstrate, and apply mathematical understanding through play, inquiry, and problem solving, and develop and use multiple strategies to engage in problem solving. Ultimately, CGI focuses on children's thinking and their ability to think and make sense of different situations and use operations, their number sense, and computation to solve word problems or story problems. Another aspect of CGI is that there are different types of strategies, and there's a bit of a hierarchy of strategies that their research has shown that children move for. So when working with a new operation or a new range of numbers, so when students move to larger numbers, they may start again with direct modeling and not automatically jump to number fact strategies. So you need to be mindful of that across the grades. So the first stage is direct modeling of actions or relations. That can be with materials, it can be with pictures or diagrams, and it can also be with your fingers. And it's the direct modeling of the process that is happening. Counting strategies are when we use counting all or counting on or skip counting strategies in the case of multiplication and division to think about the particular context or problem. And then number fact strategies are when we use facts that we know or derived facts. So if we don't know a fact, but we know part of the fact within it, we can use that to think about it. We can also use facts that we already know, single digit facts, to think about larger numbers or decimal numbers, for example. As children move through those strategies, and it's important that as we're looking at children solving questions and problems, that we know what strategies that they're using in order to support their moving forward. Another aspect of CGI, like I mentioned earlier in our curriculum, is the 3 problem types. So for addition, it's result unknown, change unknown in the middle, start unknown. It's which part of the whole that we're figuring out. So the whole is the first one, the change part, the beginning part, or the start part for an addition question. And you can see the same structure in multiplication questions as well. And this is where, again, that connection between operations, whether it's addition and subtraction, or multiplication and division, comes into play. By using these different equation types, students learn about that relationship between multiplication and division. Specifically, when we think about multiplication and division, there are 3 specific problem types using those structures. So there's multiplication, which is grouping. And that's when we don't know the total quantity. The total quantity is the unknown part. So the example, Megan has 5 bags of cookies with 3 cookies in each bag. So how many cookies does Megan have? Sometimes we use the term altogether or in all. How many, what's the total quantity of cookies that Megan has? In partitive division, and again, there's 2 types of division, partitive and measurement. And students start to learn about that in grade 3. Megan has 15 cookies. She puts cookies into 5 bags with the same number of cookies in each bag. How many cookies does she put in each bag? So partitive division is that kind of dealing out, like we're dealing out cards. We know that there's 5 bags and we want to see how many cookies will go in each bag if we're sharing them equally. The amount in each group is the unknown part. For measurement division, it's how many are in each bag that is unknown. The number of groups or how many bags we don't know. So how many groups is what is unknown. So Megan has 15 cookies. She puts 3 in each bag. That's measuring out the unit of 3 cookies. That's kind of how you can think about why it's measurement division. You're measuring out the unit of 3 cookies, and then you figure out how many bags she needs. And so there's a bit of trial and error with measurement division. We could guess, and then we could test, or we could just put them out in groups and then count up how many groups we've made. So thinking about the solution strategies, the strategies that students move through as they're thinking about multiplication and division problems for direct modeling, they might put groups for the cookies. They might have their 5 groups and they put 3 in each group, and then they count up how many they have. So that has some counting, but it's actually the direct modeling, the grouping with the materials or with tally marks. That is a grouping strategy. That's direct modeling. Same with measuring, taking the total number of counters, that's known, and then putting them in these sets. So in the groups of 3 for that particular cookie problem. Partitive, again, is like dealing them out. And again, it's done with concrete materials or with tally marks or some other sort of diagramming that students might do. It's modeling the context and the actions in the problem. Counting in multiplication and division problems often looks like skip counting. So counting by multiples. So counting up by 5s or counting up by 3s. And then sometimes students don't know the sequence fluently, so they might count up by 5s to a certain point and then count on by 1s from that. So that's sort of that bridging as students are learning their multiples. And then again, for partitive division, like I measured, there's a bit of trial and error. We know that there's 3 in each group, but we don't know how many groups there are unless we already know our multiplication facts. And we're making that connection between the multiplication facts and the total. And so we can figure out the factors. And then number fact strategies, using known facts. You know, lots of students learn their 5 and 10 facts for multiplication, and then maybe their 2s, and they can use those to figure out other facts, which is using derived facts. The process of doubling and halving and tripling and quadrupling and understanding that relationship between numbers comes into play in learning and knowing using the facts that you already know. The commutative property of multiplication. Again, you know that if you know 3 times 5, then you know 5 times 3, and students can use that as they're solving problems. And then again, that relationship between multiplication and division. So if you know your multiplication facts, that can help you with a division type question. So here, I'm going to share a couple of examples from Richmond classrooms. This first one was from a grades 2 and 3 class, and we were doing a multiplication problem. So it was a grouping problem. The total quantity was unknown. And in these examples I'm sharing today, you see another element of CGI, which is giving students the choice of numbers that they're going to work with. Sometimes you provide the numbers and we're all going to do the same numbers together. And then other times you provide a choice of numbers and students choose which numbers are a good fit for them. So in this example, on the board, I said at the farm, there are blank rows of pumpkins. Each row has blank pumpkins. How many pumpkins are there? So there's the rows, and then that's how many groups, and then each row, that's how many in each group, and then how many pumpkins are there. And you can see below, I've given the students lots of choices. And again, so that first one, that bracketed pair, be 2 and 5. So that would be 2 rows of pumpkins, and each row has 5 pumpkins. And so they might choose that. They could choose 4 and 5, 4 and 6, and you'll see that students sometimes just sort of made combinations of those. Note on the bottom in the green, there's a little 12 and 18 at the bottom. There was one student in the class, because I do tell the children, if you already know the answer, then it's really not a problem. So choose one that you're not sure about and that you need to think about, and then that is what makes it a problem. And one student said to me, he said, I already know all of those ones. I'm like, okay, well, what numbers do you think you would like to try? And so he decided on 12 and 18, which is why I just wrote it down there for him. And you'll see what he did a little bit later. So again, these are students who chose 4 and 5. And you can see. So she's first made the array up on the top left. She's organized and counted them out into rows, 4 rows with 5 in. And then she skip counted to figure out how many there were in total. So she didn't count by ones. So that was something that I was watching for. And she didn't need to touch them. She knew that there were 5 in each row and was able to skip count by 5s. These are 2 more examples, and these would be considered direct modeling as well because the students drew the picture. So in this case, the student chose 2 and 6, which wasn't one of the choices, but they made up their own combination and then needed to count those up to solve that particular one. So they bought 12 in all. And then this student at the farm, there are 2 rows, and there's 15 pumpkins in each. And then the student said, I counted, and this student, they both counted up by ones for these students. So again, there's that bridging between the direct modeling, needing to see a visual of it, and then the counting strategies that were happening. And then the student that chose 12 and 18, he used number facts. He used derived facts, what he already knew. So he did it in his head. He didn't need to create a model or create a picture. And he just came up to me when he said, I've got it, Miss Anne. And I said, well, tell me what you did. He goes, well, I decomposed 12 into 10 and 2. I did 10 times 18, which is 180. And then I did 2 times 18, which is, then he had to think about that a little bit, 36. That's 180 and 36. So 216. He said, so there's 216 pumpkins. And so this is a student who has computational fluency. He's able to decompose. He's able to use known facts to figure out other facts. But that's the range of students we have in a grade 2 and 3 classroom. They're all able to do the same problem, use the same mathematical structure, but by providing a choice of numbers, they're all able to actually have a context that is a bit problematic for them and challenge their thinking mathematically. So here's another example. This is from a grade 4 and 5 class. This is a measurement division problem. And again, there's a choice of number pairs. So have a look at what you see here. So again, similar problem. They came into the studio and we did a little notice and wonder about the squash picture up at the top left. There were blank squash. So the total is unknown. Each box has how many squash, and that's one of the number pairs. And then so what we're figuring out is how many boxes are there. You can see I've just written it each step on one line. And for students who are learning English and who are thinking about these different mathematical structures, it just sort of creates, it sort of simplifies the text or the narrative to sort of do one sentence or one statement on each line. So here we've got, for example, the first one would be there were 24 squash. Each box holds 6 squash. So how many boxes are there? I also had 128 divided by 4, and then 350 divided by 25. And again, I didn't have any students choose any extra different numbers for these, but let's have a look at some of the ways students solved this problem. You can see that the student on the left used like the long division algorithm, but then also was able to show their understanding and connection of that in different ways. Checked it using multiplication to verify their solution, which I love to see, and then also represented it with a little picture as well. And you can see the similarity to the one on the right, where they did 350 divided by 25. So how many boxes were there? They used the long division procedure or algorithm, but then also showed the boxes of 25 as well. So they're using a pictorial representation as a second way, but it really isn't showing us mathematically that they understand it. the student, hasn't sort of grouped these in any way that show us that they're showing the connection between this and the division context that was the original question. So how do we know this is 350 altogether? How do we know that there's 14? They're not grouped in any way. So that to me is what I would be noticing as a teacher. And then maybe I'm thinking about how to encourage students to record a picture or a diagram that matches the procedure or the calculations that they've done. Here's an example for a student who used concrete materials to directly model this. So he built 350 with the base 10 blocks, so 300s and 510s. And I said, so how many boxes are there? How are you going to divide this by 25? And he said, well, there's 4 25s in 100. And he's looking at the 100 square, kind of like, 4 quadrants. So there's 4 boxes in each one. So that's 4, 8, 12. And then I've got 50, there's 2 25s and 50, so that's 2 more. So 12 and 2 is 14. And again, compared to some of the students who maybe were fluent with the algorithm, to me, this direct modeling and the way the student explained his reasoning actually shared with me that he really understood the problem and the division context for this particular problem. Another student, this is all he wrote. There's his pair there. He did the long division algorithm. And I asked him if he could show it a different way. And he said, no, this is all I know. And so again, that's feedback to me as one of his teachers that we need to nurture those variety of strategies that we know tells us whether students actually understand the mathematics they're doing or not. And being able to represent something in concrete and pictorial and symbolic forms, that's in our curriculum from kindergarten to grade 12, that shows a deeper understanding as opposed to just being able to do it in one way. The same student that used the blocks also did this problem. So he did the 24 squash and then 6 in each box. And so how many boxes? And he said, Miss Ann, you need to come and take a little video of this. And so he had practiced this a couple of times, but he used repeated subtraction to show how many sixes, how many boxes there were. So I'll just see if I can play this for you if it works. Oh. So again, he said, I removed 6s 4 times, so I know there's 4 boxes. So again, very clear understanding of some different processes of that measurement division. So again, just as we wrap up this session, a reminder of where you can find some resources to support you on RichNet. If you go to Learn 38 and then the mathematics and numeracy section, and then you have all the different frameworks for the different grades, K to 2, 3 to 5, 6 to 7, 8 and 9. Under that, you have additional tiles. These practice questions are all from transitional learning. Lots of those involve CGI type questions. And then under that, there's more info, and this is some information from my district blog, but there is a page on CGI math, and it has some presentations, it has books, and it has printouts of equation cards and problems that you can use in your teaching. So as we come to a close, I'd like you to consider what can CGI offer as an approach to teaching to the diversity of students in our classrooms, what different ways might students in your classroom represent and share how they have solved a problem? What context for multiplication and division problems might be of interest to your students? And how does CGI support the understanding of the relationship between multiplication and division? Thank you for joining me.